second webinar of our series for this year. Basically, we are into the theme of this webinar series is decoding circularity. And as part of this webinar series, we are looking at different aspects of circularity and trying to help the populace understand the different elements that might be going into ensuring the right ways of circularity, what can be expected, what everybody's role in this activity is, and also simplify many of the jargons that might be in the system. So, okay. I have a comment which says that you can't hear. So, are the others able to hear me? That
we are able to hear you, Mani.
okay? So I guess whoever put up that note, please can you please check up your ring, please? Okay, thank you. So the series aims to deep dive and explore all aspects of circularity, including the core concept, implementation across industry, regulatory framework, etc., and also into the how do we drive the adoption of circularity among all sections of the society. Okay. And many times we are looking at different stakeholders, we are looking at different fractions, difficult fractions of that. And how do we look at the future trends when it comes to shaping circularity? So in this process, this is the fourth season that we are running. And in this fourth season, this is episode 2, season 4 of all of us who are now familiar with the streaming process. So this is episode 2 of season 4, where we are talking about recovery of rare earth elements from the electronics waste. Now, all of us are prey to mobile devices, and and when we are using these mobile devices, they vibrate, they do various things. So there are these tiny little elements that go into making all of these simple features that are possible, which we take for granted. So there are rare earth elements. Like Eniko told me a little earlier, some of these names are like I need to learn to speak them. Dysprosium, terbium, and neodymium, etc., etc. I don't think I said the last one right, but still, I'm sure you will help me out in pronouncing them right. These are not some things that we normally speak in our day-to-day conversations. But these elements, which are mighty rare on the earth, are the ones that are useful in multiple products. It is in mobile phones. There are some things in your wind turbines when you're talking about renewable energy. Okay, and many of us are nowadays moving towards using electric vehicles. So again, you find them there. A lot of magnets are using them. If you recall recently, especially in India, uh, electric vehicle production has actually been downsized in this year, in the last month and the future now, because of China clamping down on shipments of rare earth materials to us. So a lot is going on with these metals, and the question is, okay, what about the metals that have already been mined, that have been used in the products? Are we able to take them out? Now, that is a key question. Can we do this kind of an urban mining as we talk about it, and reuse them potentially into when you're producing new products? I guess that is the key question that we would like to look out for an answer for. Now, in this entire process of discussion, what one definite element that one needs to remember is that these programs or these awareness programs, we are very, very thankful to our sponsors, Apple, Dell Technologies, Canon India, and to Cisco for enabling these programs to happen. And also, as knowledge partners of the WEEE Forum, we're also happy that a member is here to talk to us about these metals and how we can go about the recycling of these metals. So without taking too much time from the speakers, let me go forward with introducing the previous speakers. We have today two key speakers. One is Dr. Bishu Karmakar. Dr. Bishu Karmakar serves as the member secretary of the Tripura State Pollution Control Board, which is headquartered in Agartala. And in this role, he oversees pollution monitoring, regulatory compliance, and environmental quality management across the state. Under his leadership, the board has advanced initiatives in air and water pollution control, waste management, and environmental awareness. He works closely with the government bodies, industries, and communities to promote sustainable practices and ensure Tripura's commitments to the environmental protection and healthy future. I request Mr. Karmakar to address, Dr. Karmakar, sorry, to address the audience in the webinar here and talk to us about the work the Tripura PCB has been doing on the e-waste side, and also in terms of the importance of the recycling activity, ensuring circularity as we move forward in life. Dr. Karmakar, over to you, please.
Am I audible?
Yes, sir.
Okay, so good afternoon to all the panelists, dignitaries, and participants. So first of all, I would like to convey the greetings to the all of the panelists and participants who joined in this webinar series. So, and I would really like to thanks the Karo Sambhav to involve me in this webinar series. So today's the topic is the very important topics, and I have attended so many webinars, but this is the first topic I would like to share some things. Recovery of rare earth elements from electronic waste. This is very important topics, I must say. So so before saying the recovery issues, so I just say one or two words regarding the rules. Regarding e-waste management rules. So we are all aware that since 2016, we are following a e-waste management rules 2016. So there's in these rules there are so many issues, hurdles were there. So now 2022 rules significantly tightens. I want to say the stringent e-waste governance systems. So, which highlighted the product scope, mandating recycling targets, and formalizing the producer obligations, responsibilities. So, all of the issues have been covered very nicely, especially the extended producer responsibility issues and recycling targets, mandating recycling targets. So, however, so all the stakeholders, we are working on it, so that the rules can be implemented effectively and the waste would be managed properly. So the electronic waste basically enriches various issues because it is not like the municipal solid waste. It is not like that other wastes, because it is a precious waste. I would like to say that it is a costly waste. Because waste is not that costly, but it is very costly in the sense that so many things can be recovered from the electronic waste. So so today's we are discussing about the rare earth elements. So we are all aware that those who are dealing with the especially chemical engineering or chemistries, they are well known about the rare earth elements. By name, it is rare. That means it is very rare in the earth crust also. And to mining the rare earth crust elements, it's very difficult and it is very cost effective. It is very environmental hazards also. So so the discarded electronic gadgets or electronic items. So there are basically computers, fluorescent lamps, and so many electronic gadgets. So rare earth elements are present in these electronic wastes. Basically, there are, I think, 16 to 17 numbers of rare earth elements are there. So among them, mainly neodymium, dysprosium, europium, and yttrium. So those types of rare earth elements are present in the electronic waste. So if we discuss the importance and necessity of the recycling of the electronic waste, so especially the main issues lies with the resource conservations. So that is which helps our finite resources of our earth crust and reduces the environmental impact of mining. Secondly, I want to say that supply chain stability. That means it stabilizes the rare earth element supply chain and also stabilizes the rare earth elements prices also. And third issues may lies with the environmental protections. That means mining of the rare earth elements can be environmentally damaging, and recycling from the rare electronic waste, it reduces the environmental hazards. So that means if we encourages, if we started the recovery of the rare earth elements from the electronic waste, it reduces the new mining activities. So we are all aware that mining activity is a huge environmental hazards, and lots of issues are lying with that. So if it is available, if it is available in the electronic waste, if it is can be recovered scientifically, so that will be very economic benefits we will get from that electronic waste, and which we can say that as circular economy, it will help a lot. So the recovery, though it can be, but the recovery of the rare earth elements from the electronic waste, it's not so easy. It involves very careful and very scientific methods should be followed, because lots of chemical methods are being involved for the recovery processes, like acid leaching and solvent extraction, and so many chemical methods are involved. So what about the India context? So I think informally recovery of rare earth elements are being carried out, but I want to say that informally, but lots of research and lots of innovative and lots of R&D activities is required for that, and there are lots of challenges also because rare earth element presence in very small quantities and which is technically and economically very difficult. So such kind of activities needs more investment in research and activities. I want to highlight in these issues, because those who are the bulk manufacturers and bulk large manufacturers of electronic items, so they must invest. I want to say not invest. They must incur some allocate some funds for the research and development issues for universities and the technical institutions, so that they can make some innovative and make some environmental sustainable technologies, so that it can be recovered easily from the electronic waste. So whatever the data reveals that India, our country, generates over 1.7 million tons of electronic waste annually. Though it so actual recovery rates remain very low if we consider the rare earth elements recovery. So some organizations like CSIR, BRC, they are doing, an IIT. Some IITs also involved in this their R&D activities. So they've started their activities regarding the recovery of the rare earth elements. So to achieve, I just want to say that to achieve the self-reliance in rare earth elements recovery in India, a multi-approach should be there, focusing on exploration, strengthening process, capacity building, and promotion of the more recycling units, and innovations, collaborations, and public-private partnerships. So such kind of which must be economic viability. So such types of efforts should be there, and I think regarding that recovery of the rare earth elements, I don't know is it in our country, is there any policy regarding the rare earth elements recovery policy, or especially I want to say that mineral missions or any metal recovery policy if it is in the country. So there must be inclusion of that recovery of the rare earth elements from electronic waste. So in such policy, the topic should be there included so that our every states should follow such type of policy very nicely and effectively. So from this, these are my views. Just I just shared my some views. So if we consider, if we talk with our states, Tripura is a very small state. Our electronic waste generation is very low. Basically, in government sectors, I want to say that in government sectors, maximum bulk generator is the government sector, because in our states, no manufacturer of electronic gadgets items is there directly. Some assembling, one or two assembling units are there. Apart from that, the channelization in our states is in the pipeline, because from Pollution Control Board, we have engaged one agency. In the last 3 to 5 years, Sambhav was that agency which have been finalized through the through the maintaining all the Godal formalities. So they have been authorized to collect all the electronic waste from the government sector and as well as private sector, if some private agency willing to give them the electronic waste. In our states, there is no refurbisher, there is no recycling units as such. So that is channelized through their recycling units. So as such, I want to say that in our states, government has also Directorate of Information Technology. They have also framed a policy regarding how to electronic waste can be managed, can be channelized, can be properly implemented in the states. There is also policy also regarding electronic waste. So we are also carrying out lots of IEC activities also involving some eco clubs in the states and involving some NGOs also. And Sambhav is also doing some IEC activities on regular basis. Periodically, they are also doing. So I want to just conclude my views. So it's a very good topics, and I must compliment Sambhav to conduct such a good webinar regarding that important issues, recovery of rare earth elements from electronic waste. So I just hope that the discussions will be very helpful for all the stakeholders. So thanks a lot. Thank you very much.
Thank you, Dr. Karmakar. Thanks for your views, and I'm sure with the kind of knowledge that you have exhibited in these few brief minutes regarding rare earth, and many times it is very rare to find somebody in your position even talk so clearly about e-waste and circularity, and your understanding right up to the rare earth and the rare earth extraction and the different rare earth metals that are around, and how to make sure that the supply chain stability and price stability can be maintained. I think the state, the Tripura state, is really lucky to have you there, and we are also very, very thankful to you for allowing us the privilege of serving the state and helping the collection of e-waste from your state. Thank you very much, sir. Thanks for your views, and I'm sure. And when we talk through the panel discussion here, I'm sure we will also be highlighting, and in fact, maybe I should talk about it here, that we are actively working with IIT Roorkee in terms of trying to find ways and means of extraction of rare earths from the magnets that are being used in for various purposes, be it computers, be it EVs, etc., etc. So we are actively working on such projects, and hopefully the industry will also now come together thanks to the supply chain destability that has happened recently. So thank you once again. Thank you very much for joining us and sharing your views here. I would now like to move on to introduce Eniko Hajosi. She's the technical advisor since 2014 and is part of the technical department of the WEEE Forum. She's an expert in the WEEE sector and in the operational and legislative aspects of the WEEE management, which is WEEE value chain, reporting, auditing, etc. Eniko has previously worked as the operations manager of the largest Hungarian WEEE PRO. Her unique blend of on-ground operations experience, auditing credentials, and technical leadership on EU projects make her a key figure driving innovation in electronic waste regulation and suitable resource use. She will be speaking to us about the permanent magnet project and the broader ecosystem as far as the rare earth metals are concerned. Over to you, Eniko.
Thank you very much for the kind introduction, and thank you very much for inviting me to this very interesting webinar. Let me start by sharing my slides. I have prepared some slides. Just a second, please. Into the beginning. Can you see my slides now? Are you able to see the slides?
Yes, yes, yes.
I'm putting it in. Okay, so I'm going to be talking to you about the permanent project, which is one of our projects, and I will also talk to you a little bit about the EU environment for rare earth elements and critical raw materials in general. So let's get started. So what is the WEEE Forum? I'm working for the WEEE Forum, as I said, now for over 10 years. And WEEE Forum is an association of PROs. Now, PROs are producer responsibility organizations. Maybe you heard about this. This is a kind of organization that was set up by producers to make sure that they comply with the legislation that was set up by the EU for the collection of WEEE and the recycling of WEEE. So they are obliged through the principle of extended producer responsibility to collect the WEEE that was generated by the amounts that they put on the market. And they created these usually non-profit associations, which take care of these obligations in their names. And we are an association of such PROs in Europe and around the world. We have been working for over 20 years on this topic, and we have followed through the WEEE legislation, the European Union's legislation on WEEE. Since the beginning. The first one was launched in 2002, in 2002, the second one in 2012, and the new one is coming up hopefully in 2026. So as we are working with the PROs together, we are also involved in many projects. And one of our projects is connected to the critical raw materials, to magnets. So I wanted to give you a little bit of overview of what's happening in the EU, or how the EU is handling the critical raw materials supply problem. And so, yeah, we know that the critical raw materials for the EU mean that they have high economic importance because they are used in various applications that are very, very important for the green transition, which means, the electrification of and the green renewable resources that are being applied in the EU. And of course, in electric vehicles, in the defense, applications as well. So in many, many areas. And the first list of the critical raw materials for the EU was launched in 2021. And 2 years ago, they launched the latest list. So this means that they identified 34 elements in the periodical table, which are critical for the EU, meaning we need them, but we don't have many of them because of different reasons. So the different reasons means, for example, that we are lacking natural resources within the EU. So if you see on the left-hand side, the picture shows some of the materials. So the Europe's dependence on Chinese resources for these critical raw materials. And this is for 2024. And as you see, for heavy rare earth elements, we don't have any. So at the moment, we are importing 100%. So this is a dependence, of course, that is very alarming. Magnesium, 97%, light rare earth elements, 85%, where neodymium, so the magnets are included. So the EU had to do something about this. What did they do? They launched the Critical Raw Materials Act in May 2024, which focuses on reducing the reliance of single suppliers and increasing the domestic capacities for extraction, processing, and the recycling of these materials. And of course, we come in on the recycling part. So this is where we are interested and we are involved. Other acts or other legislations which are connected, which strive to mitigate this problem, is, as I mentioned, the new WEEE Act. So this new WEEE legislation that was last launched in 2022. So we are waiting for the update, which will come out probably next year. They are now in preparation, and they are doing an evaluation of the previous legislation. And we can say that from the conversations that we are having with the European Commission and the information that we hear, probably CRMs will be some CRMs will be obligatory. Extraction will be applied to some CRMs which come from WEEE. So we really have to prepare for this. Our PPRO members have to prepare for this because they will have to require their subcontractors, the recyclers, to do such a work. And they are also working, I mean, the EU is also working on developing the Circular Economy Act, which will more focus on creating a single market for waste and creating demand of secondary raw materials, so setting the stage for this internal system to work. And here's where the permanent project comes in. So the EU, when it's trying to shape the direction in which it would like to lead its politics, it has some fundings available, and it makes it available to consortiums. So it calls for tenders. It puts out calls for tenders, and through the different agencies and different topics, they make available funding for the development of certain topics, of certain areas which are in their interest. So one of them was one of the calls was put out by European Health and Digital Executive Agency, for which there was a consortium formed, which we were part of it, and we got the financing, which is over 20 million euros. We will have to carry out this project in 40 months. With the 32 numbers that we are working on this together with, and the focus is rare earth element permanent magnets from mining and for end-of-life products, so WEEE and electrical vehicles. So this is the project I will be talking to you about. And magnets were mentioned a little bit previously, but I thought it would be good maybe to just show what these really are. So what permanent magnets are these 4 magnets that you see on the screen, of which rare earth permanent magnets are neodymium magnets and samarium cobalt magnets. So the neodymium magnets are neodymium iron boron magnets. And as you saw, neodymium is as a light earth element. So 85% of this is imported from China, and boron, I think 95% is coming from Turkey. So we really have to focus on recycling. As I said, recycling is going to be one of the aims of this project that we are working on. The characteristics of the permanent magnets are a little bit different than normal magnets, than electromagnets, and this is why they are special, and this is why they are there in some applications which are newer, because they save space, they are more efficient, they don't need magnetic properties, and they just work for a longer time. They are stronger magnets. So in today's applications, in some of them they are indispensable. So for example, in wind turbines, in MRI machines, and in other applications in the WEEE sector. So this is where we come in. These are just some examples where you can find permanent magnets, usually neodymium, can be also samarium cobalt magnets. So they are there in hard disk drives, in small electric motors, in loudspeakers, let it be in the laptops or in screens or TVs, in earphones, in e-scooters, so in the wheels, in washing machines with the latest technology, not all of them. So just some of this. And these are the partners we are working with on this project. So we are from a wide range of industry partners. There are magnet producers, permanent magnet producers. There are permanent magnet processors, so who actually have testing or final technology for the processing of secondary, so end-of-life magnets. There are some accelerators. There are some research companies, universities. There are some car manufacturers because electric vehicles are in the picture. So very wide range of stakeholders to make sure that the project is successful. The ones that are in a square are our members, and this is why they were highlighted, because we have 4 of them working on this, representing the WEEE recycling sector. So what is the actual aim of the project? It's a quite wide range, because what we are trying to do is actually ensure a resilient supply of rare earth element permanent magnets in Europe. So we want to do this by establishing an innovative network of EU actors. So you need to create an integrated value chain, but you need to do this through having new equipment, new technologies, research and development services, expertise in processing, expertise in mining, in the mining industry. We have some mining partners as well, because mining is also included, not just the end-of-life elements. And, you know, we want to create the whole ecosystem. Some relevant stakeholders you can see on the screen, of course, end users, mining industries, investors, but very importantly, policymakers, very important, regions, you know, where the mines are or where the WEEE is collected. So everybody has to be on the same page. It has to be brought together, because there is no value chain right now for the permanent magnets in Europe. So what is the structure? How are we going to do this? We thought that there would be good to define 3 hubs, which will be around 3 different topics, which are part of this ecosystem. So there will be a sustainable supply hub, which means that they will be looking at mining sites where concentrates and minerals can be taken from, not in Europe mainly, but also from outside of Europe, so third parties who are alliances. And also they will be looking at unlocking reserves, EU reserves, by testing different technologies to extract rare earth element magnet minerals from tailings, mining tailings. So something that is already there, but, you know, has not been checked. There are many innovative technologies where from the tailings different materials can be extracted, so not just from new mining. Then the second hub deals with demonstrating long and short loop circular recycling. So there are 2 ways to process the end-of-life magnets, permanent magnets, and one of them is long and the other one is short loop. So we have different technologies. So there will be magnets extracted from the different WEEEs, for example, by our partners. And they will be sent for pilot and testing activities to different universities, to different companies who already have the technology, and they want to test it, pilot it, and bring it up to at least TRL 7 level, so technological readiness level 7, which is very close to already the industry level. And by this, you know, they are trying to prepare the secondary magnets from secondary resources to be ready to be taken to Hub 3, which is an innovative, efficient, and sustainable PM magnet production. So of course, if the magnet is not coming in its pure form, it's coming from a different form, you have to work on the quality, on the grades, on making sure that there is, efficient and sustainable magnet production going on from these sources as well, with the already existing magnet production facilities. So this is how it's all set up. Of course, there's a lot of other elements. So there will be market and framework enablers. There will be business plans to make the whole platform run in the long term, to provide in the long term also R&D capabilities, investment boosters, accelerators for spin-off companies, for example, that come out from these researches and tests. Some of the activities that we will do will be, of course, first mapping the environment and the resources. Then we will organize, of course, a collaborative research and development and supply ecosystem. So we bring together all the stakeholders. We establish a value chain of supply and demand from secondary sources, because you need a critical mass to be able to establish a market. If there is a scattered amounts here and there is not going to be ever a real established market, supply and demand. There will be pilots and demonstration activities testing different processing, manufacturing pilots, including, so within this, there will be 3 scalable innovations. I will be talking about one of them in the next slide. And of course, there is also this service, this help to how to accelerate these leading edge innovations and make them available to the market so that everybody can start such an activity. So one of the things that we as a WEEE forum are working on is in Hub 2, because we are focusing on the recycling from WEEE. And we are building a digital platform to become the meeting place for magnet demand and supply. So this is going to be trying to build the place where you can sell or buy the permanent magnets that you need. So it's going to be focusing on rare earth element magnets, but later on maybe it's going to extend to other kind of rare earth elements as well. We are also developing an industry protocol, which will include identifying where these magnets are. They are very scattered. There's not very much information or not clear information on which there is, because in some products it's there, a different model of products, it's not there. It depends on a lot of on what the characteristics of the products are. And also we are trying to include in this protocol on how to manage, how to collect, how to handle, and how to remove these magnets so they can be made available on the market. This is kind of a help for the recyclers to get into this business, to start this activity, so that they can assess, what it involves and how can this be made economically feasible. Because one thing is that there will be an obligation maybe to extract it, but on the other hand, of course, it needs to be economically feasible. That's a very, very big drive for the industry partners for getting into this activity. And along all of these, we are doing this collection pilot that, as I mentioned. So we are checking at our partners' facilities and sampling them and trying to build up a database on the products where these can be found. And when we found them, we ship it for the next pilot activities. Just one more slide. Okay, my slide is hidden, so I will just explain this without the slide. There is also a magnet labeling standard being set up by the EU, which is in line, of course, with all of these activities. Where they are describing minimum amounts of magnets for products, and if they are within these limits, then they will have to be labeled. So they will have to be somehow indicated that there is a permanent magnets in a given project, if the permanent magnet is sort of considered big enough to be extracted, then it will be easier to extract it. There will be extraction instructions on how to take them out from the WEEE for the recyclers, and this standard will come out in January, I think. It's going to be part of the Circular Economy Act. It's going to be yes, it's just a reaction to one of the paragraphs in the act. You know, it had to be done. So it's going to be really making the extraction of the magnets more more easier in the long term once it's being employed. This is all I wanted to say about the permanent project and the rare earth elements in Europe. And if you would like to follow our project, please subscribe to our newsletter or follow us in LinkedIn, or simply drop me an email if you would like to get in touch or, you know, would like to know more. Thank you very much. I don't know if we have time for questions or that was in the plan or not, but I'm very happy to answer any questions.
Thank you, Eniko. I think there is a question, but then just before that, I really want to thank you for this fantastic education that you gave on the scenario that is there about the magnets themselves, as well as the enormous supply chain dependence that we have on a single source, as you rightly pointed out, and the importance of becoming independent of the single source in the supply chain, and the amount of value that exists in tailings. I just read the other day that in one of the mines that we have, there's somewhere about 4 billion worth of value that's left behind in tailings. Now, these are huge things, and I guess very valid, very, very important that we go after all of these. Because at the end of the day, we are looking for this small, rare quantities of these rare earth materials, and at the same time, industry and consequently you and me, we always look for economic viability. And if it is not economically viable, it's not going to go too far away. So, so thank you very much once again for joining us and walking us through this. I'm hoping that you're staying through the webinar because we have a panel discussion coming up. I know we are a fair bit short on time. So I wouldn't take too much time. I'll hand it over to Shivangi, and I hope the panel members and the audience stay back a little to enjoy the the rest of the program. Shivangi is part of Karo Sambhav, and she's a specialist in the APR policy in the fields of e-waste, and she's done her master's in environmental science, studies in resource management from Delhi School of Sciences. So I'll just hand it over to her, and let's go ahead with the panel. Go ahead, Shivangi.
Thank you, Mani. And thank you, Dr. Karmakar, and thank you, Eniko, for sharing your perspectives on both what is happening on an India context when it comes to collection and recycling of e-waste and recovery of rare earths from them, and also what's happening at an international scale. I'd like to invite my panelists today. We have Ayan, Barman, and Dr. Komal Tripathi as our panelists today, both experts in their respective fields. Ayan is an international relations researcher at ANANTA Aspen Center, focusing on the geopolitical implications of critical minerals. He holds a BA in Liberal and Humanities Studies from Roorkee University, where he studied global security dynamics. He has contributed to policy reports at NITI Aayog and authored articles on geopolitical issues with the Observer Research Foundation. He's dedicated to enhancing India's role in global governance and promoting sustainable development in critical minerals. Dr. Komal Tripathi is an assistant professor in the Department of Chemical Engineering at IIT Roorkee with research spanning catalysis, reacting engineering, electrochemistry, and machine learning. With a PhD from IIT Delhi and prior experience at Honeywell UOP, she brings deep industry and academic insight. Dr. Tripathi is also associated with the Center for Sustainable Energy and has received several national and international accolades. So Dr. Komal, Mani pointed out right at the starting that for a lot of us, we don't quite know what rare earth elements are. And for a layperson, while we have established that they're important, but what role do they play in what are rare earth elements and what are critical minerals? If you could just provide some context, some basics to that.
So good afternoon, everyone. First of all, I have the bad throat today, so thank you for tolerating me with this bad throat. So okay, and am I audible clearly? Okay. Thank you. So if you talk about the rare earth, as earlier panelists and speakers have also explained about the what are the rare earth basically. So when we talk about the rare earth elements, so like if you talk about the India scenario for the rare earth metal, so of course, India has the abundance of rare earth sources, and after China and Brazil, we can say. And but why it is called as a rare earth? And because although these are abundance in India, but due to the like their distribution over the earth crust, these are called as a rare earth elements basically. And if you talk about like so India resources and what are the like major challenges in those rare earth elements or the recovery in the rare earth elements. So like if you talk about the Indian resources, so they have the low grade core. And the second thing is, many radioactive materials are surrounded with this rare earth elements. So due to these complex distribution, so the extraction of these rare earth become very complex, very difficult. And like if you talk about the category of rare earth, so these are divided in like lighter rare earth elements or the heavier rare earth elements also. And by the fundamental definition of the rare earth, if you talk about, so rare earth are mainly a group of 17 chemically similar metallic elements, where 15 are mainly lanthanides. And if you talk about, so the two are the scandium and yttrium are also included in this. So these are the 17 critical elements we can say in the rare earth. And why these are the role of rare earth is becoming very important when you talk about the low transition towards a low carbon economy. So in that case, this role of rare earth elements are very important. And if you talk about the challenges in context to India, so this rare earth element extraction, these involve a complex value chain. So including the first step is mining is important, then beneficiation is important, then extraction comes into the picture, then separation is there, refining is there, then finally the product application is there. So this is a complex value chain involved in the rare earth element. And if you talk about the usage of rare earth, so more than 80% of the rare earth, those are utilized in making the permanent magnets, as the earlier speaker have has given a lot of about this permanent magnets, and what are the different composition, what kind of rare earth elements are available in which magnets. So she has given the great insight on that. And so if you talk about the specifically the use of rare earths in the magnets, so these are mainly the neodymium, dysprosium, terbium essential. These are the very essential for the clean energy and technologies if we talk about. And if we talk about the India's capabilities for handling of these rare earth elements, so although we are very abundance in the rare earth, but we don't have the developed technology how to recover, how to first thing is how to handle these rare earth element, including all the hazardous component. So this is the first thing, and we don't have the technology available to for the extraction of this rare earth element, specifically the individual metal separation, the purity of metals. Although we are dealing with so many technologies, I'll discuss later that, but we don't have
Thank you, Dr. Tripathi. Ayan, my next question actually is for you then, because given the context that Dr. Tripathi has set up, that India, while has the reserves for extraction of rare earth, we have enough reserves. Given their location, distribution, the quality of materials we have, the other elements found nearby, it is difficult for India to extract whatever is available right now. So what is India's current position when it comes to where we source our rare earths from, whatever rare earths we source?
Yeah, I mean, first of all, a big thank you to Karo Sambhav for having me on. It's a pleasure. Um, I think when we talk about anything geopolitically related to rare earths, we always begin with China. You know, we are, as of today, 97% of our rare earth oxides come from China. I believe last year it was about 12 kilotons that we got in rare earth oxides from them. 8 kilotons probably NdPr carbonates, the other four DyTb oxides. Now, the whole automotive industry shock that took place because of Chinese export restrictions. A silver lining through all of that was it helped India to sort of like shift its priority and move towards domestic resilience. When we look at foreign actors, I think Australia is one of our better partners. There have been a lot of conversations about how we can utilize the Quad, which is essentially a strategic partnership between the US, Japan, Australia, and India, and how we can refine that further into a more critical minerals based platform. So while we have companies such as Linus, an Australian-based company, they're currently, I think, granting over 200 million US dollars towards Malaysian refineries, which indirectly supports India in terms of its permanent magnet supply chain. So another aspect that we are exploring is the Central Asian corridor. Kazakhstan is coming up as a huge partner for us. So the challenge still remains that even though we do have international alliances and strategic alliances, I should say, our own domestic resilience is something that India is working on. And when we talk about that, we talk about recyclability, circularity. The challenge roots from what I would personally think is under regulation and lack of investment. So I think Miss Eniko mentioned EPR, for example. I think for us, EPR mainly comes from battery waste management rules, which was, I believe, 2022. Now, while EPR is sort of a environment compliance based mechanism, it does have a lot of shortcomings, and I do just quickly want to get into that. I think there's a lot of informal sector dominance that's currently taking place. I think 70% of our spent batteries still go through unregulated scrap dealers. There's a very high taxation and logistics issue that takes place as well. You know, we have elevated GST on recycled batteries, we have scarce reverse logistic hubs, and so on and so forth. And that in itself makes investment really challenging for private players. So when you do have such issues of enforcement, of funding delays, I think it asks for a more broader reworking of how we want to de-risk the sector. So if I could give a quick example, there are foreign recycling firms such as Redwood, which is based in USA, Nevada. We have Umicore in Belgium. We have Lithium Cycle, which is, I think, a Canadian American based company, which deal with recycling of rare earths and battery manufacturing in general. So a common theme between all of them and Western companies in general is that there is a inherent trust between the government and the private sector. And that cohesion sort of leads to very heavy investment for sure, but also the manner in which it's phased out, that is also very important. So for example, for Redwood, I have it right here. So they received a $2 billion DOE loan. For Umicore, it was a 350 million euro loan from the European Investment Bank. And similarly for Lithium Cycle, it came $475 million from, again, the Department of Energy. Now, just one thing that I would like to really, put across is the basis of financing that they do. So for India, typically, when we look at financing, we have a tranche system, we have PLIs, so on and so forth. For them, it's more based on milestone concessional financing. Now, while it does appear very similar on paper, it's actually a more de-risking form of granting loans. So like, for example, a project that has to start in the US, for example, in terms of recycling, they will make sure that there is a continuous soft financing or a system of loans and grants with very low interest and long tenure that is specifically designed for a risk heavy sector. Now, while with India, it's more to do with subsidies, it's more to do with capex, it's more to do with cash incentives, while recognizing that, okay, yeah, sure, great, we have these steps that we want to meet, we have these goals we want to meet, we have to kind of realize that mining and recycling in itself is a very long-term investment. And this is like decades in the work. So I think there is that lack of understanding that's missing. We have viability gap funding, but that's often delayed as well. But yeah, I believe that there needs to be a bit more cohesive pull between the the primary private sector and the government. So yeah.
Absolutely, Anne, and it's a very important point that you've brought up because not a lot of people think about it. And the moment you get into the space of raising any sort of money for investing into these technologies, that is where you face the issue. So, on that, actually, as Dr. Karmakar also pointed out, the best way of finding these rare earths is to find the old devices and recycle them, right? Dr. Komal, before we get into the financing of these technologies or financing of any of these systems, I want to understand what is the state of the recovery technology in India. Where are we going ahead? And if you see any certain gaps, both from a perspective of just technological capabilities and also from the perspective of the drive that private party or public party has in developing these solutions.
Sure. So this is a very good question. In fact, so now I'll briefly talk about in India, we need the threefold approach for this recycling and recovery of these e-waste. So first thing we can say that this is the direct recycling of pre-consumer rare earth elements available, and the second thing is urban mining of the post-consumer. That is Ayan was talking about the end of life products we can look after, and the third thing is the merging of this urban waste as well as industrial waste if we can look after. So threefold approach is there, and the circular economy concept is very important when we are talking about all the approaches. Suppose there are multiple technologies right now we are dealing with, whether if you talk about the rare earth extraction or the any other kind of e-waste extraction also. So there are multiple technologies available, like direct recycling is there, but certain advantage and disadvantage of all the technologies. If we talk about the hydrometallurgy, so if we are treating like 1 ton of e-waste, then 3 lakh tons of wastage of water is there in hydrometallurgy. And at the same time, if we talk about the pyrometallurgy process, so in the pyrometallurgy process, due to the harsh conditions of this temperature, intensive conditions of this temperature and pressure, these things, so these harsh conditions are there. And then if you talk about the direct recycling, so direct recycling is also there, but it is also not available to treat the e-waste in a large quantity. So these are the major challenges. And if you talk about the major technologies, so all these are acid based approaches, so they are using very concentrated acid to leach the metals. So right now, not specifically focusing on the rare earth, but we have developed we have done a lot of material engineering in that sense, and we have developed some deep eutectic solvents where we can minimize this towards this development of the green solvents, where deep eutectic solvent has good potential. But what is happening, all those are good in the lab scale, if you say. So these all are available. These all efforts are at the R&D scale only. So we need to there are a lot of challenges where we need to look after the roadmap or deployment side from this R&D scale to industrial scale. What are the major challenges? How either one thing is, can we direct switch to the green solvents, or the second thing is, can we can we see the synergy between how can we minimize the concentration of acid what we are using, or can we regenerate that acid? So these are the multiple things are there where we need to consider. And the last thing is very important, the techno-economic analysis is very important, and it is important at both the stage. The first is at the very early stage, that is a very critical stage. Here the techno-economic energy analysis is very important, where we can directly eliminate some of the processes before doing a lot of R&D on that. And at the later stage also it is very important when we are commercializing the things. So this is the thing I would like to say. And the important parameters, if you talk about, so temperature, pressure, reaction time is there, leaching efficiency is there. And if you talk about the DES, so viscosity of DES is a major challenge right now. So deep eutectic solvents, they are working fine, but it is very difficult to make the deep eutectic solvent of less viscosity, because ultimately we need to treat it with the solid things, and if viscosity is high, then we need to give a lot of mechanical energy for that. So how can we make a deep eutectic solvent less viscous? And then the role of this digitization is playing a very good role here. So like we have developed one model for specifically for lithium ion battery, where if you put any kind of like deep eutectic solvent, what are the deep eutectic solvent, where we are mixing one hydrogen bond donor with one hydrogen bond acceptor. So we have designed a tool where you can put any hydrogen bond donor and any hydrogen bond acceptor in this tool, and this tool can give you the resultant viscosity and the pH where it can be treated. So this is specifically focusing on lithium and battery only right now, the stages. And this, without doing experiments, due to this we have developed the data driven approach. Yeah, this can give you the viscosity of the resultant component.
And Dr. Tripathi, this must also help a lot, because when we are talking about something like waste, we are not talking about a homogeneous input. Waste,
Yes.
even permanent magnets, the different places they are found, their compositions or their size, their coating
Very
on the top of them, whether
heterogeneous.
there's nickel coating or not, it differs quite a bit. So this must also help in sort of creating those permutation combinations, because that is one of the challenges of scaling a technology. How do you deal with the variability of your feed?
Yes,
If
yes.
your
So we are
feed
trying to
changes,
develop.
output
Yes.
changes.
Yes, we are trying to develop those. Ultimately, our aim is to minimize the experimentation part. We are doing the experiment, but how we can minimize the experiment? So number of experiment can be minimized from these approaches actually. So these deep eutectic solvents people have designed for multiple applications, not exactly for rare earth, not exactly for e-waste management, but for other applications. So for that, this fundamental or nowadays, this is a very buzzword like physics inspired neural network. So you have all the fundamental properties of particular that green materials. You just develop a physics inspired model, and after that you end up with like 4 or 5 experiments you need to do. Out of like 50 experiments, at least you can minimize 45 experiments with this data driven approach only. So
That is
digitization is also very important concept. And then LCA at the end, life cycle analysis is also very important. So it is completely missing. And when you see how what is the global warming impact, because ultimately these things we are doing for the transition towards the low carbon economy, for the transition towards the greener economy. So for that actually LCA calculation and from cradle to cradle calculation is very important here. One thing is cradle to grade, but cradle to cradle where we are considering all the scope emissions. 3 scope emissions are there, S1, S2, and S3. So sometimes based on only S1 scope emissions, we can say that we are saying that the model is green. But we need to evaluate S2 and S3. Those are the indirect emissions. We need to evaluate those also, because otherwise we could not know that actually the process is green or not. So we need to evaluate the if we are using the electricity, what is the source of that electricity, whether it is the grid based renewable electricity or we are utilizing. So these things are very important actually.
no, but having a data-driven approach also then makes the cycle of iterating a lot quicker as well, which allows for more innovation, because you don't have to go through the whole process of starting from scratch. But that actually also introduces a certain level of risk for anyone who's looking to scale this up. And Ayan, this is something that you very briefly touched upon, that there's a certain amount of risk that comes with deploying, piloting, and then scaling up new technologies. So what role do you think policy, for example, would play here? And what role would the more information into how carbon neutral these technologies are, how much that information would aid, say, foreign investors in becoming more interested in driving these technologies being piloted?
Oh, I mean, I think the primary reason for lack of investment, particularly in mining projects from the private sector, has been due to lack of knowledge. I mean, you look back a year, there were, I think, 3 to 4 mineral auctions that were revisited, redone over and over again. Just because, I mean, we need upgraded technology. Tech collaboration with Japan is something that has been sought after for a while. I think we need to improve GSI techniques to identify where to mine exactly. I think that is a major challenge why, major companies such as, because the intent is there, the Adanis, the Vedantas, they all want to invest in this, they want to be part of tech development. I'm not a technical expert, but as Dr. Tripathi also mentioned, there needs to be an advancement in R&D. And if that comes from international collaboration through maybe Japan or Vietnam as well, I think their seabed mining is something that is, I think, decades ahead of a lot of countries in the world right now. So there's a lot we can learn clearly. But as you mentioned, it's about stronger domestic policies as well.
True, and especially when we are not only talking about mining from virgin resources, we're specifically talking about waste, urban mining, what we call urban mining, and this being such a, compared to mining, which is still more localized, urban mining has a little bit more complexity to it because your source technically is distributed all over the country, right? Your waste is distributed. So collecting it enough back and then getting enough volumes to be able to then extract material in enough volumes that a manufacturer can use it is where some of this scaling up complexity also lies. Because
Yeah.
as, for example, Tripura being a state that is a hilly region, it's a smaller state, you can't necessarily, for example, get solutions for every state. So getting enough financing to even touch those areas and getting collection from those areas and then accumulating it is very, very tricky for sure. Sure.
Yeah, and so sorry. I just wanted to quickly add to that. So for, geographical challenges such as that, I mean, you look at other countries as well in Europe and the US, and there is a difference in terrain, maybe not as drastic as India, but there does exist that problem there as well. I think one solution to that could be implementing a single central nodal agency. It could be under, maybe an up and coming, company such as Atero. It could be Batex Energy. It could be under the Ministry of Heavy Industries as well. The point is there should be a hub and spoke system which is properly modeled, properly regulated, which can address these challenges. Because the whole challenge of, topography, that basically reduces by 50% just by having a well-established hub and spoke model system. So that's definitely something India should, look into.
Of course. Thank you. Thank you so much, Ayan. With that, we'll actually open the floor for some audience questions. We have some questions in the chat already. One of the questions actually Eniko answered, which was regarding why so much of the conversations for rare earths ends up revolving around permanent magnets. And as Eniko responded, they are an extremely important part for advanced technologies and clean energies. But another question that Vibhor Bhatnagar shared was on issues relating to lithium recovery and how one can overcome them. So Ayan, Dr. Komal, Eniko, anyone?
Sorry to interrupt, Shivangi.
Yes.
Well, we get to answer that question. I guess Mr. Jha has been raising his hand and waiting patiently for the past half an hour or so. So it'll be great if you could pull him in later. Okay, thank you.
Yes.
So can you repeat the question second? That is related to something lithium-ion battery or?
Yes, it was regarding lithium-ion batteries.
And what is the exact question?
Issues related to lithium recovery and how we can overcome them.
Okay, fine. So I would like to talk about like lithium-ion batteries. So there are different chemistries available in lithium-ion batteries itself. So if we talk about the general lithium-ion battery where lithium, nickel, cobalt, manganese are there. So there is a main issue. If we talk about, there are two approaches. One is the acid-base approach we can follow. And when we are considering the green approach for lithium-ion battery recovery, so the problem is all the major green solvent, they are working in the acidic zone. And when we try to change their pH from this acidic zone to basic zone, then their material structure could be disturbed. And if you talk about the lithium, so lithium could be precipitated at around the 12 pH. And other metals available in this lithium-ion battery, nickel and manganese, so they are around like nickel, cobalt, and manganese, they all get precipitated around 4 to 6 or 7 pH. So making that pH in the very basic condition, initially we need to consider the like a solvent in a acid pH or around the neutral pH, and then suddenly we need to drag the pH from this 6, 7 to 12. So this is a major challenge when we talk about the hydrometallurgy approach for the lithium-ion battery. So that's why people are moving towards the pyrometallurgy or the combination of hydro and pyro for specifically for the lithium-ion battery, we can say. So that's why we are recovering this lithium-ion battery in the form of lithium carbonate, Li2CO3 form. So and yes, there are challenges in the recovery of this metallic lithium right now, and these are on the R&D stage only. Yes.
Thank you, Dr. Tripathi. I'd like to invite Dr. Animesh Jha. If we could give him access to speak. I don't think he has the access to speak right now.
Yeah, I'm sure.
Okay. While that is being implemented, I think we could briefly take another question. Syama Lenus has asked, and I think Dr. Animesh has also partly responded, on how can one get such technology or information so that we can reduce the number of experiments that we need or iterations we need to get to a particular scale. Not just developing the technology, but to get to a particular scale of implementation.
Hi, can I go ahead and ask?
Yes, sir, please.
Thank you to panelists and to very articulate speakers. I have been working in the areas of rare earths since 1998, since I joined the University of Leeds here in United Kingdom. I'm ex-graduate of University of Roorkee, now IIT Delhi, IIT Roorkee, and know colleagues. I think I have met also Dr. Tripathi recently, 2-3 months ago, while I was visiting IIT.
Yes, sir, we met. Yes.
So let me tell you a couple of very important things for the general audience. Some of you may not know. India was one of the largest exporters of rare earths before 1990s. The plan for not exporting was implemented when late Professor Satish Dhawan became the scientific advisor for the Prime Minister, because he recognized. I knew Professor Dhawan quite well because I was studying at IIC Bangalore, so I know. And then China was also rapidly producing, so China became the global exporter. About India's resources, India has huge resources of zircon, which contains rare earth, and India also has huge resources of monazite, which is what Komal was mentioning, that they have radioactive materials. Predominantly, they are alpha emitters. Because they are alpha emitters, they can be stopped even using a piece of paper. But the perception of radioactivity is very, very complex in general public. And that perception needs to be also understood. These two rare earth, radioactive uranium and thorium, extremely useful material. They're primary source of also a fissile material. Okay. And India is one of the leading countries in nuclear technologies in the world now. So coming to technologies, Bhabha Atomic Research Center has some very good technologies. And people don't know about it, but I know about it. Because Bhabha Atomic Research Center has been developing since the center was developed. What is important, we don't have tonnage scale, and that requires now going on to some of the upcoming technologies, some of which Dr. Tripathi talked, and it requires rapid acceleration. It also requires investment, subsidies, very, very important, which Mr. Ayan Barman articulated. So these are very important steps. We are University of Leeds, Karo Sambhav, our spin-out company from University of Leeds, IIT Roorkee, Professor Nikhil Dhawan, the director himself, expressed huge interest in type of things we are doing with Karo Sambhav and IIT Roorkee. We have a completely new technology and it's very green, some of which we will discuss later on. And I would encourage Dr. Tripathi to work closely with Professor Dhawan, because two of you can really push the technology boundaries, and with University of Leeds and other colleagues. This is very, very important, because if you want to drive a train for innovation, you have to have signal, you have to have an engine, and you have to have fuel. Please remember this. And if you don't have these things, you cannot drive innovation. And that Mr. Barman and Sri Ganapathi ji mentioned that, policy is very important. So policy is also very important. I think our Hungarian colleague, she also mentioned, Eniko mentioned, policy is important. So we have been quite fortunate to develop some very clean technologies. And I think, Eniko, I would contact you also, and we should look at, because Europe is also trying to collaborate with India. There's a policy level discussion. Prime Minister and the President, they met together not very long ago. And there's some special programs being developed within EU, and we also need to look at that. Thank you.
Thank you so much, Dr. Jha. It's always a pleasure talking to you. And as you pointed out, India holds a very unique position when it comes to rare earths, because it's not as if we don't have the capacity to be one of the leaders in this space again. I would like to thank all of the
Shivangi,
speakers. Yes.
just 1 second. I just want to let the audience know that we had the privilege of hearing Dr. Jha, who's in the School of Chemical and Process Engineering, University of Leeds, and one of the renowned experts in this field. And he was very modest about his introduction. I guess if we start talking about the kind of work that he has done in the field and others, we can have maybe 100 to 150 page book just about the kind of work that he has done. So thank you very much, sir, for your patience, for following us the webinar for this long, and also providing us your inputs. We are very, very grateful. Thank you very much.
Yes. Thank you so much, Dr. Shah. And I'd like to thank all of our speakers and panelists, Shri, Bishu Karmakar, Dr. Karmakar, Eniko, Hajosi, Ayan Barman, and Dr. Komal Tripathi. The key things that I think that we all should take from this particular webinar is, just like anything, rare earth recovery from e-waste is a complex conversation, but what it needs is people to talk across the aisle, talk to each other. It is extremely important as we get towards a space of more of a digital India, and if you want to become self-reliant in manufacturing of products, we need to figure out where our rare earths are coming from, because relying on any one particular source for anything is always a recipe for instability. So I hope you all had a wonderful time today. I would like to thank our sponsors once again, Apple, Dell Technologies, Canon, and Cisco. Please stay in touch as we continue on our journey on decoding circularity, and a very, very good day to all of you.
Thank you very much. Have a great time and have a great day. Thanks for joining, everybody. Appreciate it. Thank you, Eniko. Thank you, Dr.
Thank you.
Tripathi and
Bye-bye.
Dr. and Ayan. Thank you very much. Bye bye.
Thank you so much.
Thank you. Thank you. Bye bye.